Okay, hello everyone. My name is Zhenan Zhang. I'm Dr. Yan Yuchen's PhD student. Today I'm here to going to show you how to use Abaqus to finish a simulation. And here is your case one for homework one. This case will introduce you how to use Abaqus to finish a very simple simulation. So in this case, you will learn how to run the simulation step by step from very beginning to the end. Even though this simulation is a very simple case. However, for some other complicated simulations, you can always follow these procedures. Just change the geometry, change the material property, and change the meshing tab and change the step. Okay, before we start doing the case, let's have a very brief review of this case. So in this case, and at beginning, you need to create a geometry. It's a rectangle with it's a plate with a circle. It's a geometry in the part, and then give a material property to this geometry. And after that, then the assembly. Assembly means just insert this part geometry to the assembly step. And this step, it means what kind of simulation you are going to do. In this case, it's a static general simulation, but for some other, maybe for example, the impact, the high velocity testing, usually we use dynamic, explicit. And then loading condition. Here, we apply a pressure on the top, bottom, and fix the bottom part. The pressure on the top and meshing. I think in Doctrina's previous class, he has mentioned what's the meaning of mentioned. Why the simulation is called FEM simulation. It means in the FEM simulation, we usually cut or divided this kind of geometry into a lot of very, very small pieces. And these small pieces have some common points. They connect with each other. So after using a lot of equation and a lot of very heavy communication calculations, you can calculate the size or the deformation of this geometry. And finally, you can submit your job and finish the simulation. Okay, this is a very, very quick, brief review of this case. Now, let's go to the software. So before we start, I just hope to make sure everybody has installed and downloaded this software, because the time in this class is really limited. So I don't think we have enough time to help you install this software step by step. I spent almost 1 hour to finish this installing. But no worry, I have created a checklist for this case. Here is the website. You can go to the website to download this software. Just make sure to select the student version after 2023. Yeah, also made the checklist to help you guys finish the simulation smoothly. I have shared this checklist in my website. You can go to Zhenanzhang, the bio to get this checklist in the simulation part. Okay, now this case is clean. Since I have installed and downloaded this software, I just marked each part. And so are you ready for the simulation? Okay, that's nice. And choose Abaqus CAE. Here is Abaqus CAE. And click. Okay. We have opened Abaqus CAE. In the first step is the geometry modeling. It means we need to create a geometry for our simulation. Here is the heat. Create the model on 2D planar on the size 4. Here is the create part, 2D planar, and the size is 4. Continue. And then we create lines, rectangles, negative 0.3, negative 0.4. It's first point, and the second one is 0.3 and 0.4. Okay, let's do it. Here, create lines and rectangle. The first one is negative 0.3, negative 0.4. And the second one is actually this point. Actually, should be this point. But I think I recommend you input here because sometimes you can not that accurate, not be that accurate. Maybe make some mistake and here 0.3, 0.4. Okay, now we have this rectangle. Hit create circle. Input 0, 0. Rectangle 0, 0. And 0.1. Now we have it 0.1, right? Yes. And hit this crossing and down. Crossing and down. Okay, now we have this geometry. So let me know if you have any question. Okay, now we have finished this geometry modeling, and then we define the material property for the geometry. Choose property. Property, create materials, and mechanical elasticity and elastic. Create materials and mechanical elasticity and elastic. And for the Young's modulus, here only need to define two material property, the Young's modulus and Poisson ratio. Young's modulus 209 and Poisson ratio 0.3. Okay. And create section solid homogeneous. The section means we have the material property, but we also need to define what kind of materials you have defined. Because for the solid homogeneous means in each direction of the materials, it has the same material property. And also need to check the plane stress string thickness is 1. Even though it's a 2D simulation, but You can also define a thickness for this plate, for this surface. And here the section. Oh no, no. You need to create a section, homogeneous, and materials, and this one. And then you need to assign this section on this material property to our geometry. Here, assign section, assign section here, and click your geometry down, and yeah, this section. Now you can see your geometry change color from a little bit red to green. When you see this color, it means you have assigned this material property to the geometry successfully. Now you have done the geometry part and the material property part assembly. Since you only have one geometry here, so in this assembly part it's quite simple. You just need to hit the instant part, and it's okay. Yeah, assembly and instant this part, and don't forget to click independent. It means you can mesh in this candle assembly directly. Okay, and now is the next step. So you let's study and what you are going to do to run is a kind of static general simulation. It's a kind of low velocity uh, simulation. But for some very high velocity testing, uh, it's a kind of a dynamic condition. It's a little bit complicated. For this static simulation, is maybe it's the simplest. It's a quite a simple one. And here, step. You need to create a step. The static generator is a default one and static. Okay. The time is one, time period one. Actually, this time period is not real time for your it's not real time. It's just for the simulation time, so it's one. Okay. Okay. Yeah, another step is quite important. You need to define the boundary conditions. In the upper simulation, boundary condition sometimes is a difficult part in the simulation, especially for some very complicated geometry. If you cannot define the boundary condition well, you cannot even run the simulation. I have came across a lot of this kind of conditions. I cannot run my simulation. I don't know what happened. I don't know the part. So for this time, sometimes I need to define my boundary condition again and to need to fix this problem. So here, just follow me. Follow this checklist. You'll be okay. Here, load. Choose load. Create load and pressure. Top boundary. Negative 1000 magnitude. Okay. Here is your geometry and the load. Create load. Pressure and continue. Top boundary down negative 1000. Okay, now you have this. You can see some arrows. And then boundary conditions. Boundary conditions. Oh, for the second part and for the third part, it's a definition. It's a kind of boundary condition for your bottom surface, not for your bottom surface. to fixture. It means to fix your geometry in this area. No movement in x direction and in y direction. Here, boundary condition, displacement rotation, and the bottom boundary U2. U2 it means y direction. 0, okay. Create boundary, displacement rotation, continue. Bottom boundary, down. U2, 0. It means no displacement in the y direction. U2y. Okay, now it's good. Looks good. And again, because now we have fixed the geometry in the y direction, but we also need to fix it in the x direction. No display in x direction. So, oh sorry. What we should do? Boundary condition and displacement rotation and lower right corner. U1 0. Here, boundary condition, yeah, displacement, and the right corner, right bottom. What I see? Lower right corner, here. Now, U1 0. Okay, that's good. Okay, now you have your boundary conditions. Okay, now you have your geometry, you have material property, you have defined the step, the static general step, and the boundary condition. Finally, meshing. Let's see how to do the meshing, how to divide it, your geometry into a lot of very small parts. Split your geometry into small parts, super small part. Mesh. Assign element type. At the beginning, you need to select a kind of element type for your meshing element plane stress. Okay, let's see. Here, here, mesh. Assign element type. Here you need to do is you need to select the plane stress. It's a default one, and you also need to unmark reduced integration. Yeah, actually, sometimes if you select reduced integration, and I think maybe simulation result is not that accurate. So just unmark it. Okay. Now you have already selected the element type and mesh control in the mesh control to 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 select the element shape. Sometimes it's a rectangular or triangular. Here use a chord. Mesh control chord. Okay. And then you need to define the seed part instance. It means what the size for your meshing element. Uh, if this element, sorry, the meshing element is too small, you need a very, very powerful computer to run it. It is also very time consuming. For our simulation in our lab, some simulation may run almost a week or 2 weeks, very heavy. So here, the global size 0.04 seed per instance here. And 0.4. 0.4. Apply. You can see some circle here, small circle here, and you can also see some rectangular, some square geometry on the corners. Okay. Okay, now we have the side of the element, we have the tab and the shape of the element. So you can mesh your geometry. This one. Mesh part. Yes. Now you have split your geometry into a lot of small element part. Small element. Now you have almost finished every steps in this simulation. The next one, run your simulation. In the job, choose job, create job, and submit your job. Create job and continue. Okay. This the job manager. Submit. Yeah, the time for the simulation it quite depends on your computer and your geometry. If you have a very good computer, it is super fast. For this case, because it's very simple, I think everyone's computer can run it super fast. So now the case has been completed. You can check your result directly. Just click the result. Yeah, inductions slides. It shows to choose visualization of file. Open 1, 2, 3, 4. You need to click 4 times. And here, just result. You got the result. Plot your counters here. Here is the stress counters. But in the slides, I think there is a requirement for your counters. In the small string analysis, the strike counter plot should be made on undeformed mode without showing element. In this case, here you can see the stress counter is very simple. It's very smooth. So how can you get it? It's a deformed counter with a lot of black lines. These black lines are the edges or the boundaries of this element. So you can hide these lines here. Common option, feature edges or no edges, both okay, feature edges. Compare with the contours in the slides. In our case, it's still it's not that smooth. It's not that smooth. It's very rough. So here, in to do is click the contour option, continues, apply. Now it looks much better, right? Much better. The final one is undeformed. Yeah, this part is not easy to find. I also spent some time on Google to find how to get the undefined model. Actually, here it's a plot counter on deformed shape. Just hold. You can see there's a plot counters on undeformed shape. Now you get it. Yeah, and the doctor also recommended you to change the maximal missile strikes and the minimal missile strikes. You can change by yourself and to get a much better, much beautiful counters. Okay. Okay, that's the case. And I will upload this video in the website and also upload it. I will also upload this checklist on website. You guys can check this checklist, and just follow the step by step. I promise you can do it. If you have any questions, stop by my office. My office is wall building, not wall building. Yes, wall building 206. Wall building 206. Okay, good luck, everybody, and see you in tomorrow's class. Bye bye.